There we go. All right, Chemistry 3101. Today we're going to start with hydroboration oxidation. And if you remember our last lecture, we looked at the Markovnikov addition of water across a double bond, across an alkene. And we said we could do the Markovnikov addition of water using just an acid catalyst. But the problem with that, a catalytic amount of acid and water, is that if carbocation rearrangements could happen, then they often do, and then you're going to end up with mixture. So we said, okay, well, there's a way to circumvent that, and that is to use oxymercuration demercuration, which again affects the Markovnikov addition of water and avoids any carbocation rearrangements. Well, if you wanted to do the anti-Markovnikov addition of water across an alkene, and sometimes we want to do that, you have to use this process, which is covered in section 8.7, which is called hydroboration oxidation. It's a hyphenated title and it's a two-step process. Okay, it says here hydroboration oxidation adds the proton and the hydroxyl from water with an anti-Markovnikov regioselectivity. Now I think that my students are pretty good on Markovnikov regioselectivity in the last lecture. So we learned the rule that with Markovnikov addition, it's the rich get richer, right? The vinylic carbon that possesses the most hydrogens accepts the hydrogen. Well, what we see in anti-Markovnikov addition, if I look at this vinylic carbon, it has one hydrogen, and this vinylic carbon has two hydrogens. So now we're going to see the opposite. Instead of the hydrogen going on this carbon, the hydroxyl is going to go on that carbon, and that is anti-Markovnikov addition. So anti-Markovnikov. Now again, this is a two-reaction sequence. You actually have to write down step 1 and step 2 very clearly. If you put all of these reagents in the same reaction mixture, all you're going to get is a soup, and it's not going to work. Okay, it's going to give you nothing. So the first step is BH3.THF. Now you might be wondering, what is all this? Okay, well, BH3 is a compound you might have seen in general chemistry. It's called borane. Maybe yeah, maybe no. You might have seen it when you were learning molecular geometry or something, and you said, okay, well, it's, you know, trigonal planar, maybe something like that. But BH3 is borane, and THF is tetrahydrofuran. And tetrahydrofuran is this, okay? It's a cyclic compound that has an oxygen in the ring like this, tetrahydrofuran. Tetrahydrofuran is one of the most commonly used solvents in organic chemistry, okay? It's used a lot in organic chemistry. Now you might be wondering, okay, well, that's cool, borane and THF, tetrahydrofuran, but what the hell is this dot that's kind of floating in midair? Well, we're going to cover that in a second. But the second step is H2O2, which is hydrogen peroxide and sodium hydroxide. And we're going to look at each step, mostly the first step, I would say, and figure out, you know, why this reaction reacts with anti-Markovnikov regioselectivity. Now, again, in our textbook, it covers both of these steps, the whole mechanism in dirty detail. I'm probably not going to ask you the mechanism of hydroboration oxidation, but it's a good idea to understand it so that you will understand why we get anti-Markovnikov addition of water across the double bond. Well, besides the regioselectivity being anti-Markovnikov, we also have to take into account the stereoselectivity of this reaction, right? Because we're adding two components. We're adding a hydrogen and a hydroxyl. And if you're wondering, what do you mean by evaluating the regioselectivity, or sorry, the stereoselectivity, Mr. Dion? Let me show you. If we have a double bond like this one here, and this is 1-methylcyclohexene, well, when we add the hydrogen and the hydroxyl, they're added in what's called a syn fashion. Syn means nothing more than the hydrogen and the hydroxyl are added to the same side, okay? You could say same side. We usually don't say the same side in organic chemistry. We usually say the same face of the molecule, okay? Right, think about it. This carbon is sp2 hybridized. This carbon is sp2 hybridized. They're both trigonal planar. So the double bond is planar. And so the hydrogen and the hydroxyl can either add on the top, as is shown here, right? They came in from above, and that's why they're both on wedges, right? They're pointing up. Or they could have both been added, again, syn. That syn fashion means on the same face where they're both pointing down. I have the hydroxyl pointing down and the hydrogen pointing down. Notice, again, that the scientists wrote the products out, the two enantiomers, correctly, and that The regioselectivity is also correct, right? This is anti-Markovnikov, right? The hydrogen is going to the carbon that is poorer in hydrogens. It's got none, anyhow. But again, the hydrogen and the hydroxyl are added in a syn fashion. And so if you were to draw either of these, okay, these are two enantiomers as well, but you see what's wrong with these products is that the hydrogen and the hydroxyl are on opposite faces of the molecule. When two groups are added on opposite faces, two opposite faces of the molecule like this, we call that anti-addition. So anti-addition. So what's the take-home message for you guys, for my Chemistry 3101 students, is that you need to know that hydroboration oxidation regioselectively is an anti-Markovnikov addition of water across a double bond. It's a two-step process. The first step is borane and THF mixed together, and that's why there's that little dot there. And again, we're going to talk about that more in a second. And the second step is to treat it with hydrogen peroxide and sodium hydroxide. And the hydrogen and the hydroxyl are added in the syn fashion. They're added to the same face of the molecule. Well, I promised I'd talk to you a little bit more about BH3, right? Borane. If you look at the geometry and the hybridization of borane, well, borane has the same hybridization as a carbocation, right? They're sp2, okay? So this is sp2, just like the carbocation is, right? If you look at the electron configuration of boron, it's 1s2, 2s2, 2p1. Then what's the word I'm looking for? You hybridize those orbitals in order to make an sp2 orbital. Anyhow, so you hybridize those valence electrons to make an sp2 orbital. They each have one electron. Anyhow, I shouldn't need to go over that with you. We covered that in chapter 1. But anyhow, you see that it has an empty p orbital. That's where I was going. Okay, so we have this big empty p orbital here, and so the borane can function as a Lewis acid. It can function as an electron acceptor. What's interesting is if you just take borane BH3 and put it by itself in a bottle, okay? If you just have, a pure sample of BH3, so BH3, what it does is the borane will actually react with another molecule of borane, and what it does is you see it exchanges these electrons to make what's called a 3-center 2-electron bond. So there's a dashed line that's missing here in this structure, okay, in these two resonance structures. So you end up with this here, which is again a 3-atom or a 3-center 2-electron bond. Sometimes we call those banana bonds. Now, banana bonds are never going to come up in this class, okay? I'm never going to mention a banana bond ever again. All you really need to know from this slide, you guys, is that whenever we do a hydroboration oxidation in the Klein textbook, which is what you're going to use 90% of the time, okay, we use borane THF, okay? That's what we use for step 1. However, in the ACS study guide, so I know that a lot of you have an ACS study guide and have taken a look at that. What they use for the first step is, instead of writing BH3 THF, they write B2H6, right? Which is essentially this guy right here, which is B2H6, okay? Which we sometimes call diborane. Anyhow, that's the only time you're really going to see that. So the diborane, okay, that gets formed when we mix, or when we have a pure sample of borane, is stabilized in an ether solvent, right? THF is an ether, right? You can see that THF is a type of ether, an ether, right? Because an ether is when you have ROR, well, you can see the ether right here in THF. And so what happens is the lone pair from the oxygen dumps electron density into that borane, into the borane, and it forms this stabilized compound here, okay? So that's our active reagent. It's this Witter ion, okay? It's got, a positive charge and a negative charge in the same species. Anyhow, so that is what we use as our active reagent, is the borane THF, okay? That's always going to be your step 1 when you're in class with me. But if you're studying ACS materials, sometimes you might see B2H6, which just represents diborane. If you're surfing the internet, looking at things about organic chemistry, you might see the same thing. Okay, so here's the mechanism. Okay, now I wrote here specifically that you don't have to memorize this mechanism. However, each step along the way should make some sense. Now, in terms of that regioselectivity, why do we get anti-Markovnikov addition? Well, there's two two ways we can explain this. We can either use electronics to explain it, or we can use sterics to explain it. I would say that if I was to ask any of my former students who are A students and say, you know, why does borane add, you know, regioselectively such that we get anti-Markovnikov addition of water, I guarantee you that 90% of them would say it's a steric consideration, because I think it's the easiest one to remember. But if you look at the first step in the mechanism, okay, if you follow this mechanism that I have written out here, you see that we have addition of the hydride, okay, so we have this bond being formed here, okay, while we have this double bond coming out and dumping electron density into there, right? Remember that there's an empty p orbital on this boron, so it's available for electrons. So when this bond or this interaction is formed here, and it's kind of drawn here as a dashed line, right? What you're going to do is when you form that bond, you would end up putting a partial positive charge on this carbon. Well, that carbon is going to be more comfortable with a partial positive charge than this one would. So that's the electronic consideration, okay? That's why we end up with the borane or the boron being attached to the least hindered carbon. That's the electronic consideration. Now, the steric consideration is a lot simpler, I think, okay? Especially if you're just learning organic chemistry. I mean, you look at this carbon, it's more sterically hindered than this vinylic carbon, right? And I should have just circled one, but you can see that this is more substituted than this one. And so the BH2, right, is going to get attached to the side that's least hindered. So that explains why the boron gets attached to the least hindered carbon. And the boron eventually gets replaced with a hydroxyl, okay? And that mechanism is covered in our textbook, but I'm not going to go over it with you right now because I'm not going to ask you any questions about it. You can take a look at it. If you take organic chemistry for chemistry majors, we do cover that mechanism in detail in that class, but in non-majors, we don't. And it's not, they don't ask you about that mechanism on the ACS final either. Now, in terms of the stereospecificity, I find that this is pretty, you know, a lot of my students have a good intuition about chemistry or organic chemistry at this point. And so since this first step here, where we end up with the hydrogen and the boron being added to where the double bond was, right? Since it occurs by this concerted process that is shown here, you know, it all happens at the same time, okay? Well, because of that, it makes sense that the hydrogen and the hydroxyl are going to be added at the same face of the molecule, right? Because this is all occurring at one time. Okay, the hydrogen is getting added here, the boron is being added here, and again, I told you that the boron just ends up getting replaced by the hydroxyl. And so that makes sense as to why the hydrogen and the hydroxide, or the hydroxyl, are added to the same face of the molecule. So if we have a molecule like this one here, again, you see that the double bond, both carbons are sp2 hybridized, both are trigonal planar. That's why they've drawn it on this kind of sheet-looking thing here and here. Well, the hydrogen and the hydroxyl are going to add with an anti-Markovnikov regioselectivity, but in terms of their stereochemistry, they're going to both add with Syn addition, meaning they're both added to the same face of the molecule. Now, there's sometimes when we have to be really careful in evaluating the stereospecificity, other times where we don't have to be as concerned with it. For example, if you end up with a compound that has no chiral centers, well, in that case, it doesn't matter at all. You know, you just draw the anti-Markovnikov addition product and don't even think about it. And in our textbook, he gives you an example where there's no chiral centers formed. But what if you had a molecule like this one here, right? You get anti-Markovnikov addition. Well, since we can get Syn addition of the hydrogen and the hydroxyl, right? They could either add to one face or the other. In that case, you end up with one chiral center, right? And you're like, well, the hydrogen should add right to the same face as the hydroxyl. Yeah, but this isn't a chiral center, right? This is not a chirality center. So in that case, you would just end up with a racemic mixture. You end up with a 50-50 mixture of each enantiomer. But what if you did the Syn addition, right? Anti-Markovnikov Syn addition, and the hydrogen and the hydroxyl are added in an anti-Markovnikov fashion. And what if you end up with two stereocenters? Well, in that case, you end up with a pair of enantiomers, right? Again, look at this double bond. Okay, here's the double bond. you see that this hydrogen and this hydroxyl added anti-Markovnikov, right? This is the richer one in terms of hydrogens, and that's where the hydroxyl went. And you see that they're both pointing down. They're both on dashes. It's a Syn addition. Here, in the second molecule, they're both pointing up. Okay, and we end up with a pair of enantiomers, right? So this is a great question. I can tell you that I don't have the entire ACS final memorized, but I remember I have a few questions memorized, and one of them was a question almost identical to, not this really, but if you go back to the very beginning of this section, they had a question like this, you know, and they said, well, which ones are not possible products? And you'd have to know that, you know, Markovnikov addition, that is anti, is not going to be a product. Anyhow, with all that in mind, that's quite a bit of information about hydroboration oxidation. Let's give it a try, and let's try to answer this question. It just says predict the product or products for the following reactions. You see we have a beautiful double bond here. The first step is treatment with borane and THF. The second step is treatment with hydrogen peroxide and sodium hydroxide. Again, this mechanism is covered in our textbook. I didn't put it in the slides because I'm not going to ask you about it directly. Feel free to take a look at it. Again, the more you know about mechanisms, probably the easier it gets. And if you're wondering, you know, Mr. Dion, I thought you said that you would explain something about mechanisms to help us understand. Well, what I can tell you is that the only mechanism you really need to understand the regioselectivity and the stereoselectivity is the first step. Okay, that's why I have that one in my slides. Anyhow, I digress. Well, could anybody tell me how many stereocenters would be formed once we do the anti-Markovnikov addition of water across this double bond? I'll draw the only vinylic hydrogen that's in here. Could anybody tell me how many stereocenters you'd get? While I'm doing that, I'll just redraw the molecule. No? Yeah, you'd only end up with one stereocenter in this case. Right, let me prove it to you. Okay, let's say you added the hydrogen and the hydroxyl on the same face of the molecule and they were both pointing up. Well, then you'd have the hydrogen coming up like this, and you'd have the hydroxyl coming up like that, right? I know there's a hydrogen going in the back, okay? What if they were both going down? You had the hydrogen going down, you have the hydroxyl going down, right? That's from, again, the Syn addition, and of course, there's going to be this hydrogen here. Well, how many stereocenters are there in these molecules? This, okay, this is not a stereocenter, is it? It's not a stereocenter because the pathway going here or going here is identical. And so that is not a stereocenter. So we've only got two products. We got the two enantiomers, right? And we could even delete these just to make it a little bit prettier and say all we're going to end up with are these two compounds, which are enantiomers of one another, right? So we end up with enantiomers. Enantiomers. There we go. Let's take a look at the next one. The next one's a little more interesting because we've got a chiral center in the molecule that we're starting out with. Here's the only vinylic hydrogen. We're not doing the rich get richer. It's the opposite, right? The richer one is the one that's going to end up with the hydroxyl. So let's draw the skeleton, meaning just the carbons that are going to remain unchanged, okay? We got this guy, and then I'll just copy and paste that. So copy. There we go. Okay, so first let's imagine that the hydroxyl, oops, didn't mean to do that. The hydroxyl is added pointing up, okay? Right, there's also going to be a hydrogen that's added pointing up. That means this methyl group is going to be pointing down like that. Okay, we're also going to have the Syn addition where the hydroxyl is pointing down and the proton is pointing down like this, and that means that this methyl group would be pointing up. Could anybody tell me what the relationship between these two molecules is based off of what we learned in chapter 5? What's the relationship between these two compounds? They're not superimposable mirror images. You know, they're not non-superimposable. They're not mirror images of one another, are they? but they're non-superimposable. So they're stereoisomers that aren't enantiomers. Therefore, they are diastereomers. Okay, these are diastereomers of one another, stereomers. All right, maybe we could delete those hydrogens, and maybe that would clear it up. Okay, delete anything that's unnecessary. Did I put a hydrogen there when I didn't mean to? Right, you can see that this is the mirror image of this, and this is the mirror image of that, but this one didn't change. Okay, this methyl group that's pointing up has nothing to do with the mechanism whatsoever. It is unaffected. It's not affected at all. Okay, so there we go. All right, there we have it. So nothing else to report on that one. And let's move on to the subject of catalytic hydrogenation. As I told you, there's a neat blurb in our textbook that talks about trans fats and where trans fats come from. In trans fats, if you're afraid of trans fats, which are in things like, you know, I don't know, what does he put? He puts McDonald's French fries or something like that, a picture of that in the textbook. Where trans fats come from is they come from the hydrogenation of vegetable oil. So the trans fats are unnatural. And that's why people are so afraid of them. Anyhow, and I guess they have been linked to atherosclerosis, perhaps. Anyhow, so let's move on. So we covered section 8.7, which deals with hydroboration oxidation. Let's move on and talk about section 8.8, which deals with catalytic hydrogenation. So as you can imagine, if we're doing hydrogenation, we're going to be using H2, and hydrogen is a gas, and it's a highly flammable gas, but it can be worked with, you know, very safely. There's ways to work with hydrogen very safely. Anyhow, hydrogenation is nothing more than the addition of hydrogen, a molecule of hydrogen across a carbon-carbon double bond. It requires a metal catalyst. What are the possible metals that we can use? We can either use palladium, platinum, or nickel. You're like, oh no, that sounds like a lot of different metals. When am I going to use which one? What scenario? Well, the answer is, I got some good news for you, and that is that you can use either one of these three metals for any hydrogenation in this class. We're going to assume that they're just interchangeable. You go to the cupboard, whatever you got, you use. Okay, so here they put platinum down here, but the scientist could have written palladium or nickel. Okay, you could have written any one of those. So here we have a double bond, right? We have an alkene, and we're converting it to an alkane, right? If we're hydrogenating or adding hydrogens, we're going from something that has 1 unit of unsaturation to something that has no units of unsaturation. And so now you've made something that's saturated, right? It's saturated with hydrogens. And you're like, oh, then maybe I could draw a connection between this and saturated fat. Absolutely you can. Absolutely you can. That's where saturated fats come from. Well, hydrogenation, I mean, there are natural saturated fats, but that's another topic. Okay. We'll talk about that when we discuss lipids someday. Anyhow, so hydrogenation, again, addition of hydrogen across the carbon-carbon double bond. Good news, stereospecificity is Syn. Okay, so this, with respect to the stereospecificity, the addition occurs in a Syn fashion. That means that both hydrogens are going to be attached to the same face of the molecule. Right, you see that the person treated this alkene with H2. They ended up with 2 stereocenters, right? In this first molecule, both of the hydrogens are pointing down. They didn't draw them in, right? Because the person is a pro. They're like, I don't draw this. This is bond line structure. Okay, but I'm your instructor, and I'm just going to pencil them in here for you. Right, you can see that both of the hydrogens are attached on the same face of the molecule. If the scientist had gone and drawn something, and don't draw this, okay, I'm going to delete it, or I'm going to rebuke it. Okay, so if the person had done something like this, and then the method, right, that's impossible, because that would mean that the hydrogens were added in an anti-fashion, and that doesn't happen. So if you were to draw that molecule, or it's an enantiomer, that would be completely wrong. So Syn addition of the hydrogen. Now, you guys know about catalysts, right? You talk about catalysts in Gen Chem 1 and in Gen Chem 2. You can't get away from catalysis. Anyhow, if you're wondering, you know, what do you need this metal for? What's the whole point behind this metal? Well, hydrogenation mechanism, I don't think it's completely understood. Like, I mean, I don't think that everything is known about everything, you know, every last detail of the mechanism, but I think it's pretty well understood. And what the metal does, or what the catalyst does, is it essentially lowers the activation energy, right? But not only does it lower the activation energy, but it changes the pathway slightly. So you guys know from Gen Chem 2 that if you lower the activation energy, what's going to happen? Your reaction rate is going to increase. And we talked about that a little bit earlier on in this class. So that's the effect of a catalyst. It just does nothing more than lower the activation energy and changes the pathway. Sometimes we call it an alternate pathway. Anyhow, I remember one of the first times I ever taught this class. I had a really good class, and students would always ask great questions, and they were really hungry for knowledge of the hydrogenation mechanism. So here's how it works. What these black spheres are down here, this is the catalyst. Okay, so this is the metal. This is the palladium or platinum or nickel, whatever it is, but that's the surface of the metal. Okay, so I could even write that in here for you. This is the surface of metal. Okay, and what happens is when you subject the metal catalyst to hydrogen gas, or H2 gas, is that the hydrogen gas binds to the surface of the catalyst. Okay, like this kind of looks like you got a bunch of lollipops sticking out of there, doesn't it, or something? But anyhow, you have all those hydrogen atoms bound to the surface of the catalyst. Now, this is where it'd be handy for me to maybe turn my camera on just for a second. And you know, you guys, it's tough doing this kind of stuff when you're not in class with your students. But if I had a model, okay, let's say I had a carbon-carbon double bond. Right here's a carbon-carbon double. This is an alkene, right? Alkenes are flat like a pancake. Okay, if I make a model of ethane, it is not flat, right? You see both carbons are sp3 hybridized. Both are tetrahedral. But when I have an alkene, if I have the surface of my catalyst that's got the hydrogen atoms on it, it kind of comes down like a UFO, abducts these hydrogens, right? And they're both going to be attached to the same face of the molecule. So turns it into an alkene, and then it flies away, okay? So that's why both of the hydrogens are added to the same face, right? The alkene comes down, lands, gets the two hydrogens, gets converted into an alkane, and leaves the catalyst like that. Does that help at all? I hope so. It would be a lot more fun if we were in Centennial Hall, but hey, you know, we do what we can. Da-da-da. Does that help explain it to anybody? I can't tell what you guys are writing. Okay, thanks, Alexis. Even if it helps one person, it's worth it, right? Okay, cool. Yeah, so that's why it adds in a syn fashion, why both hydrogens are added to the same face of the molecule. Might seem like a silly thing to act like it's aliens being picked up from a UFO, but I don't know. If that helps you remember it, I'll be a happy camper. If my students remember something, trust me, Mr. Dion is going to be a happy man. All right, so there's the Mr. Dion kind of explanation of hydrogenation, and that explains why it's Syn addition, right? Syn addition, both of the hydrogens are added to the same side of the double bond. And if you're wondering, hey, Mr. Dion, is that the same type of thing that we saw with the hydroboration oxidation? Yes, Syn addition, the definition is still the same. We added both components to the same side of the molecule. Now, you can imagine that in a 3000 level course like organic chemistry, you're going to run into all kinds of crazy scenarios. And I don't mean crazy, but just all kinds of variants, you know, on different scenarios that we could run into. And what if you had a compound like this? Okay, this is an uncommon compound, 1,2-dimethylcyclohexene. What if you hydrogenated that? Right? If both hydrogens add to the same face of the molecule, you end up with a meso compound in this case. So don't be drawn, you know, this and saying, hey, it's an enantiomer, because it's not, right? It's a meso compound. So in this specific case, you only produce one compound. Now you might be wondering, well, you know, is the book going to cover this? And I would say yes. I've looked through the practice problems in this chapter or in this book enough to know that Dr. Klein likes to ask all the different scenarios. So he puts them in there. Okay, he really does like to exercise your brain and get you to think about all the concepts that you've looked at, you know, and bring it into this chapter. He does a very good job of bringing things together in this class, in the textbook. All right, this is kind of an interesting table, but you got to take this table with a grain of salt, okay? Because there's situations where this table doesn't apply, but generally speaking, okay, this table 8.2, covers the relationship between the number of chiral centers and the stereochemical outcome of catalytic hydrogenation. So if you have no chiral centers being formed, then you just get an alkane and you move on with life, and you don't have to worry about dashes and wedges or anything. Right? If you end up with, if you have only one chiral center, you get 2 enantiomers. If you've got 2 chiral centers, then you're going to end up with a pair of enantiomers. But I would caution you on this one, though. I would caution you on this one because what if you have meso? Well, if you have a meso compound, you've got 2 chiral centers, but you only end up with 1 product. And our textbook even says, you know, this table is cool. I mean, he put it in there. He didn't think it was a bad idea, or he wouldn't have put it in the book. But he just says, you know, you got to stay on your toes. Okay, don't try to memorize your way out of everything. You got to understand that some cases you're not going to end up with, it's not going to work out exactly like this, but I'd say, you know, most of the time it will. Anyhow, as you can imagine, the best way to master this content is with practice. And I find that my students usually get pretty good at drawing the product of Syn Addition of hydrogenation, right? All we have to do, if you want Mr. Dion's quick and dirty way of doing this, look, just isolate the double bond. There it is. Everybody in this class can recognize an alkene by now. You're doing hydrogenation. You don't even have to worry about regioselectivity. It doesn't even come into play because both vinylic carbons are just going to accept the hydrogen, and both hydrogens are going to be on the same face of the molecule. Look, if you want a really easy way to do it, or the easiest way I can think of, draw the molecule, oops, like this, okay? I'm going to put this methyl group in like that. Maybe I won't. Okay. Look, all you got to do is this. Draw both hydrogens pointing down to start. Okay. So that means that this methyl group must be pointing up. There's one. And just do it again. But draw both of the hydrogens pointing up. So have a hydrogen pointing up like that. Have another hydrogen pointing up like that. So that means the methyl group must be pointing down. That's it, my friends. That's it. That's all, as we say in French. Okay. What's the relationship between these 2 compounds? They're enantiomers, aren't they? Enantiomers. Mers. Now, if you open up the textbook and look at the solutions manual, my guess is that he's not going to draw them like this. Okay. Because this is kind of like, I don't mean this in a derogatory way, but it's a little bit like amateur hour when you draw stuff like this. There's nothing wrong with that because you're learning. If you were to write, if we were doing paper quizzes and one of my students wrote this down, what would I give him? 100%, because it's correct. Okay, that's one of the beautiful things about teaching science. It's not about what I like. If it's right, it's right. No arguing. Okay, but if you look in the textbook, my guess, and I haven't looked in the textbook recently at the solutions, but my guess is that Dr. Klein probably doesn't write it out like this. He probably just does this. You say one methyl group pointing up and one methyl group pointing down, and those are the enantiomers, and he just leaves the hydrogens out. If you need to draw them in, you do it. Okay, there we go. I got a question for you guys. Let's see who's on their toes, and this is not an easy question. Could anybody tell me how many products you're going to get from the hydrogenation of this alkene down at the bottom? How many products? Patty, how many products do we get? Yeah. Why? Yeah, that's right. It's a meso compound. That's right. Good. Good. I'm glad you guys were able to figure that out. Look, if you're not with me, just watch. This is why scratch paper is so important in organic chemistry. Look, let's imagine both of the hydrogens are coming up. Okay, they were both added. That means that both of these methyl groups are going to be pointing down. Sorry. Yeah, this one's pointing down and this one's pointing down. What do you notice about this compound? Right, there's 2 stereocenters. Yes, this is a stereocenter. Yes, that is a stereocenter. However, this is a meso compound, isn't it? So you only get 1 compound in this case. Okay, now again, the way I've drawn it is the way a beginner would draw it. Is there anything wrong with drawing it this way? No. Okay, if I try to tell you in another life that there's something wrong with drawing it this way, you take me right to this video and say, no, you said it was okay, Mr. Dion. And I'll say, yeah, you're right. Okay, there's nothing wrong with this. I give that 100%. But I bet you that if you look in the textbook, he probably just has something like this, you know, or he just draws that, or he could draw them both as wedges, and he just says, yeah, okay, that's the product, and it's meso. Give me a thumbs up if you follow me on that. You're like, Shaw, it's only 8:40. We've covered 2 beautiful, beautiful reactions. Anybody with? All right, awesome. Well, let's switch gears and let's talk about halogenation probably my favorite mechanism in this chapter. You need to know this mechanism. Good news, if you take the time and learn this mechanism, I'll tell you one that you're going to love. It's the exact same mechanism, really, 90% similar in section 8.10. So the next section where we look at hydrohalogenation, okay? The only difference is solvent, really. So I'll show you what I mean, okay? Let's see here. How do you make PVC pipes? Has anybody here done any plumbing before? I have. I was a landlord in Montreal. I owned an apartment building there. But anyhow, and I built a bathroom last summer. Anyhow, I like plumbing. Is anybody into plumbing? Just me? Okay, anyhow. Halogenation. So if you've ever wondered how polyvinyl chloride is made, like PVC pipes, you can go buy them at Home Depot. You start out by halogenating ethylene. So this is ethylene or ethene, which is a gas. It can also be used to ripen fruit. Anyhow, we're not going to talk about ripening fruit today. But you take ethylene and treat it with chlorine, and you end up with this compound, which would be called 1,2-dichloroethane. Well, that can undergo an elimination reaction to give you vinyl chloride, and then vinyl chloride undergoes a polymerization reaction where you end up making this polymer. And we're going to talk we do a whole chapter on polymers in organic chemistry too. It's probably the last chapter we look at. It's probably the easiest chapter you'll ever cover in the class. Anyhow, so that's how you make polyvinyl chloride. I always have somebody who's fascinated by polymers. And one thing you'll notice about our textbook is I think in many chapters he has blurbs about some kind of polymerization or polymer chemistry. I think David Klein might have worked in a polymer lab at one point in his life. He seems to really enjoy that. Not as much as drugs, but he seems to enjoy it. And when I say drugs, I mean legal drugs. Okay? Let's see here. You know, when I was working in pharma, when I worked for Bristol Myers Squibb, we used to bring junior high school students in and try to steer them towards STEAM or, you know, science, technology, engineering, and math. You know, this is, I mean, a long time ago, but we'd give them this whole explanation about what organic chemistry is. We'd even talk to them about spectroscopy and teach them all kinds of things about the drug discovery process. And then you could never anticipate their questions in 1,000 years. I could never anticipate what they were going to ask. And one time we brought these students in, you know, they were probably 13 or 14. I went through this whole presentation about what drug discovery was, what NMR was, and all these different things. And finally, this guy raised his hand. He's like, yes. I said, what's your question? He's like, now, when you're talking about making drugs, are these illegal drugs? I said, no, these aren't illegal drugs that we're making here. I said, we have a saying in the lab, we make drugs, we don't do drugs. Anyhow, all right, so where the heck was I? I don't know what I was talking about. Yeah, halogenation. So halogenation is interesting in that it only works well with chlorine or bromine. Now, you might be wondering, why would it only work with two of the halogens? There's two more halogens. There's fluorine and there's iodine. Why don't they work? Well, halogenation with iodine is just too damn slow. It's too slow to be useful. And halogenation with fluorine is too violent, right? If you remember the table of standard reduction potentials from general chemistry, right? You'd remember that fluorine is the king of the castle, right? So a reaction with fluorine is just too violent. In fact, if you look on YouTube, you can find all kinds of nuts doing chemistry with fluorine. Is super dangerous. And we'll talk more about that in chapter 10, the whole reason why iodination and fluorination are impractical. Anyhow, regioselectivity is nothing more than this. If you take an alkene, okay, this is what you need to know. You take an alkene, you treat it with bromine or chlorine, Br2 or Cl2, you end up with a 1,2 addition, right? Just like every reaction we've looked at in this chapter, but it's anti-addition, okay? And if you're like, I got to keep all this stuff straight, you know, when it's a Syn addition, when it's an anti-addition, yes. But I promise you that the more you practice, the easier that will get. So what would be the relationship between these molecules? These molecules are enantiomers, aren't they? So these are enantiomers of one another. Anyhow, now let's cover the mechanism which rationalizes or provides you with a rationale as to why you get anti-addition. You need to know this mechanism. One of my favorites, okay? It's because it results in this interesting intermediate called a bromonium ion. There's one I bet you never heard before, the bromonium, okay? If you read the book, you would have heard about the bromonium, but the bromonium ion is formed after the first step in the mechanism, which is a simultaneous nucleophilic attack and loss of leaving group. But the reason why they happen together and form this bromonium ion is because this arrow represents the nucleophilic attack. This curved arrow represents the loss of a leaving group, but there's a little bonus arrow in here, okay? This is the extra curved arrow where a pair of electrons, a lone pair from the bromine, comes down and forms a bond to the other carbon. So you end up with this tricyclic, positively charged species, or I could call it a tricyclic species where the bromine has a positive charge on it, right? Tricyclic, I mean, it's, you know, this carbon, and this bromine atom, and that is called a bromonium ion. Now, the bromonium ion, since it's tricyclic, is going to point up on that one face of the molecule like that. And so the bromide, when it comes in and does another nucleophilic attack to pop open that three-membered ring, that bromonium ion, it's going to attack from the least hindered face of the molecule, right? The bromide is not going to attack from here because it's too hindered. Cannot happen. And that is why we end up with anti-addition. Take a look, okay? You can call it a backside attack, which is why we get anti-addition. So again, this is our nucleophilic attack. This is our loss of leaving group. This is the arrow that forms the bromonium ion, right? That's the one where we form the tricyclic intermediate, the bromonium ion. Once we form the bromonium ion, we have a hindered face on the top here in this case, and then we have an unhindered face down here at the bottom. And the nucleophile, which is your bromide, is going to attack from the least hindered face, and you end up with this anti-addition, which would result in a trans 1,2-dibromo. But again, it's anti-addition is what we call it. So you'd end up with this compound in the enantiomer. Give me a thumbs up if you're like, I don't think I could draw it right now. Give me a few minutes. But at least I understand the rationale. Yes, if I know what a bromonium ion is, yeah, it makes sense that the bromide should attack the less hindered face. Good. Okay. Excellent. Thanks, Megan, Jessica, Skylar, Byron, Alexis. I can't see who else is on here. Moira, everybody. Great. That's good. That's very good. So, since the halogenation is stereospecific, right? Meaning you only get anti-addition, son of a gun. It's an anti-addition only. Okay? The stereochemistry of the starting alkene is going to determine the stereochemistry of the final product. So this is one where I've seen you guys, and I don't mean you guys, but I mean some of my students get fooled on this when we did, when we took a look at, different rotamers when we were in chapter 5, okay? So see if you can follow along with me. If we just start with a cis alkene, okay? So you have cis-2-butene, right? That's a diastereomer of trans-2-butene. It's a stereoisomer, but they're not enantiomers. They're diastereomers, okay? So if you start out with the cis and you do a bromination, well, you're going to end up with these two enantiomers, right? Those two are enantiomers. Now, usually for my students, it's not that much of a stretch to go, okay, I got that bromine pointing up, this bromine pointing down, and I did the same thing over here, just the opposite, right? But you've got to be able to manipulate these bonds in your mind, right? What would happen if you rotated this bond and put those two methyl groups in the same plane, right? Then you have this bromine coming up like this, but then you'd have this bromine like that, okay? That is not a meso compound, my friend, right? There's no plane of symmetry in either of these. Okay, that's not a meso compound. And when we did chapter 5, there were some examples like this, and students were like, oh yeah, this must be meso, because they failed to rotate it and say, okay, well, it's not a meso compound, right? They were trying to envision some kind of plane of symmetry that doesn't exist here. Oops, I didn't mean to do that. Anyhow, and then similarly, if you start with the trans, in this case, okay, and you do anti-addition, right? You have one bromine pointing up, one bromine pointing down when we have the two methyl groups in the same orientation. But if you rotate this bond, you'll see that this is actually a meso compound. And if you're thinking, okay, yeah, I think I can sort this out, pretty quickly, we'll hold the phone, because what if we look at examples where we add two groups that are the same and we do Syn addition? Well, then it's flipped around, okay? And if you're wondering about what do I even mean by that? Well, once we get to the last couple sections here, when we look at what's called dihydroxylation, it will become much more abundantly clear what I mean. Okay, so you have to get used to manipulating molecules like these pretty quickly. Okay, let's predict the products for each of these reactions. You know what? I've taught this class enough. I even have a note here in my my personal notes. It says, you know, you can do this one pretty quickly, because I used to ask my students to draw this one in Centennial Hall, and they'd have it done faster than me. You know, students are very quick. So, you know, something else, I have a note here that a student tried to do this, you know, something like this. They'd say, okay, well, one bromine is going to be pointing up, right? There's the two vinylic carbons. The other bromine is going to be pointing down. Could anybody tell me what's wrong with what I just drew? I might remove like half a point from this if this is a paper quiz. There's something that's kind of goofy about my structure. Anybody? Cha? Yeah, thanks, Skylar. This is not a chiral center, right? That's not a chiral center. So why the heck am I drawing the bromine on a dash? It's I mean, it's not the end of the world. You know, it's not like the person does completely not understand anything. But generally speaking, you know, you should draw it more like this. If it's not a chiral center, don't draw it as a chiral center. So then we'd have the other bromine here and this bromine here. So the relationship between these two compounds is that these are enantiomers. These are enantiomers. And again, I'll just put this here. I'll say not a chiral center, just in case anybody's wondering. And if we look at the next one, there we go. This one, okay, so let's draw the skeleton like this. Okay, I'm just going to copy and paste that while you guys are thinking about it. Copy and paste. There we go. So look, the first one will have one of the bromines pointing up like this. The other bromine is going to be pointing down like this. That means that this methyl group must be pointing up like that. And then in the next one, I'll try to make it a little bit cleaner. The next one, we have the bromine here pointing down. And then we have this bromine pointing up, and then we have the methyl group going down like that. All right, I'll try to tidy this one up. So we have the bromine pointing down. And could anybody tell me what the relationship between these two molecules is? And it's not a trick question. What's the relationship between these two? Both stereocenters are flipped, so they must be cha-cha-cha. Anybody there? Yeah, thanks, Lauren. Yeah, they're enantiomers. Enantiomers. There you go. So bromination or chlorination. So again, where all these say Br2, that could just as easily be Cl2. And it occurs with anti-addition. Okay, so anti-addition across a double bond. Well, I promised you that when we look at Halohydrin Formation, which I thought was a completely separate section, it's not. It's the tail end of this section. If you do a halogenation reaction, so if you just take an alkene, right, like what they're doing here is if you take this alkene and you treat it with bromine, right, the first thing you're going to end up with is a bromonium ion. Well, all these reactions that we've been looking at before, they never list a solvent, but they're probably in solvents like CHCl3, which is chloroform, or CH2Cl2, which is dichloromethane. Now, he leaves those out because you don't really need to know what they are, or you don't need to know this for these reactions to work. When solvents are really important, because you're like, well, in chapter 7, we had solvents all the time. Well, that's because in those reactions, it was important whether you had a polar protic solvent or an aprotic solvent, right? Well, if you take the alkene and you treat it with bromine, but instead of having something like chloroform, right? Instead of having chloroform as your solvent, if you do the reaction in water, well, instead of the bromide coming in to react, since you're doing in water as a solvent, there's so many more water molecules than there are bromide that the bromonium is actually going to be attacked by a water molecule. Okay, the water does the nucleophilic attack, and then we have the loss of leaving group here. So you end up with anti-addition, but it's anti-addition of the bromine and water. Now you're like, well, that's an oxonium, man. Okay, I'm not going to end up with a positively charged organic molecule in the end. The answer is no. Okay, no. We end up deprotonating the oxonium with another molecule of water. So this isn't the complete mechanism. The last, so after the formation of the bromonium ion, get the nucleophilic attack by the water molecule, and then water comes in and acts as a base to deprotonate the oxonium. So you end up with anti-addition. Okay, so and you end up with what's called a bromohydrin in this case. So this would be a bromohydrin. If you tried the same chemistry with chlorine, you end up with a chlorohydrin. So what do you need to know? You know, what are the take-home messages for you guys? It's the reagents are bromine in water or chlorine and water, and you get anti-addition. Now, if you're very astute, which I know you all are, you're like, okay, Mr. Dion, this is an easy example because that's a symmetrical alkene. What if it's asymmetrical? Then is it Markov, you know? Well, if it's asymmetrical, here's the answer. Okay, and you kind of have to memorize this, and I'll cover it a little bit of detail why it reacts the way it does. But what happens is, I like to remember it this way, that the nucleophile, the hydroxyl, right, from the water, adds to the more substituted carbon. Okay, and there's a very good reason for that, right? You form the intermediate bromonium ion. Okay, there's my bromonium, and the water, when it comes in, where's my water? So if I draw a water molecule, the water molecule actually ends up reacting on the less hindered carbon. Okay. Anyhow, that's not the complete mechanism. It's shown here. And there's a very good reason for that. Watch the positive charge. Right? Once you form the bromonium, you've got the positive charge on the oxygen. And then after water does the nucleophilic attack on the most hindered carbon, I'll highlight it in green. Okay? The green carbon, we'll call that the green carbon. Well, then the positive charge is down here on the oxygen. So in essence, the positive charge got passed from the bromine through the carbon down to the oxygen, right? That's the that was the pathway, so to speak, of the positive charge, right? So which one of those two carbons, would it be the one that I have highlighted in green or the one that I'm highlighting in blue that would be more comfortable with a positive charge passing through it? It's the one that's more substituted, the one that's highlighted in green. And so that's why it happens. So essentially, when the water attacks, the positive charge kind of goes from the bromine through the carbon onto the oxygen. Now here they've drawn the transition state, right? They took the time to actually draw the transition state there, and that provides you a rationale, right? The more substituted carbon is going to be more comfortable having that cationic character than that carbon would there, right? So again, just the more substituted carbon is the one that takes the hydroxyl. Give me a thumbs up if that makes some sense to you at all. You're like, yeah, I'm kind of overwhelmed. There's quite a bit of chemistry here, Mr. Dion, but yeah, it makes some sense, right? See, this is where organic chemistry gets really exciting because not only is there a memorization component, I'm the first person to admit it. Is there some memorization in organic chemistry? Absolutely. Absolutely. I would be a fool. I would be insane to say no, there isn't. Of course there is. Of course there is. But it's logical, right? We usually try to provide you with a rationale. I don't like sometimes I have to, but I don't like just saying to my students, you know what, you guys just memorize this junk, you know, or something. It's not junk, but you know what I mean? Like, I don't like to just tell students, just memorize this and there's no rationale. You know, the first time I taught a class at UCCS, it was organic chemistry too. And, you know, it's the first class I ever taught. And we came in and we were doing a reaction and we were talking about anti-addition. And I said something anti-addition, and they knew the idea of anti-addition. It's not that the students didn't know that, but I brought up, I said, you guys remember the bromonium ion that was formed, and then, you know, it attacks from the leaf, and they had no idea what I was talking about. So, you know, and after I explained it, they're like, oh, well, that makes sense now, you know. So I like to try to clear things up for my students. Okay. Anyhow, Halohydrin Formation. So here we go. Predict the major products that are expected when each of the following alkenes is treated with bromine and water. Let me show you Mr. Dion's patented, non-patented method of solving these. Okay, this is the way that I like to do these with my students, is like this. I'm going to draw the skeleton. like this. And I like to draw the intermediate. I just do. Okay, if you're the kind of person that doesn't need to draw it, if you're just able to say, well, this is the more hindered carbon, so the hydroxyl is going to add here. If it's pointing up, then the bromine is going to be pointing down. This isn't a stereocenter, and I'm going to get this compound, and it's an enantiomer. Okay, and that is the correct answer. If you just wrote that, and if you're ahead of me, kudos, man. That's awesome. I'm happy. If you're ahead of me, great. Okay, but if you're like, I will accept your trick, Mr. Dion. Okay, here's my trick. I like to draw the intermediate. Okay, I just draw a bromonium ion. So on the bromine, you've got two lone pairs, two bonds, and a positive charge. You guys remember formal charge? So bromine has 7 valence electrons. 7 subtract 4 dots and 2 sticks gives you +1. Okay. Now this is the more hindered carbon of the two. So that means that the water is going to come in as a nucleophile, right? And it's going to react at that carbon. Okay, that's kind of the way I like to do it. I like to draw the bromonium ion with my students. Again, if you don't have to, if you can just, go for it. So let me just draw that. And this is a very simplified version, so we'll put a couple of arrows here. You end up with this compound where the hydroxyl would be pointing up, right? Because it's coming in from the opposite face of the molecule, right? Since this is pointing down, this is going to attack from the upside or the top face of the molecule. And then this is not a stereocenter. So I'm going to end up with that compound. Plus, I'm going to end up with the enantiomer. Give me a thumbs up if you follow me on that one. Okay, and if you're really confused, if you're wondering, where's the enantiomer coming from? Where does that come from? Look, it's just the same thing repeated. Okay, I usually don't do this, but I will just this one time, where you would just draw the bromonium on the opposite face of the molecule. Now the bromonium is pointing up. Okay, so now the water is going to attack on the same carbon, but it's going to attack from the bottom face. And if you're like, that's not the bottom face, Mr. Dion. Well, this is 2 dimensions. Come on, give me a break. Okay. Anyhow, and if you need to do that, you do it. Okay, as long as you get the right answer, you're happy and I'm happy. All right, there you go. And these 2 compounds are enantiomers. If you need to draw both of those, do it. Okay, it's not the end of the world. Okay, so those 2 compounds are enantiomers of one another. Anyhow, let's draw the next one. I got to speed up a little bit. I'm probably spending too much time on this. But anyhow, the reagents, again, were bromine and water. So same thing here. If we treat this with bromine and water, this time we won't draw the intermediate. We're going to end up with the hydroxyl on this carbon because it's more hindered. So we'll draw the hydroxyl pointing up, which means the methyl will be pointing down and the bromine will be pointing down. And we're also going to end up with the enantiomer in this case. All right, well, let's move on from there. And let's move on to dihydroxylation. There's 2 sections on dihydroxylation. There's a section that deals with anti-dihydroxylation, and there's a section that deals with Syndihydroxylation. After I lost my job in 2007, I interviewed a couple of companies, and one of the companies I went into, I walked in, I was kind of nervous and everything, and we ended up having a 45-minute discussion just on dihydroxylation, ways to do dihydroxylation. So there's a lot of different ways, but I'm going to show you 2 ways. One way to do anti-dihydroxylation, right? Add the 2 hydroxyls on the opposite face of the molecule. And I'll show you a bunch of ways, but probably one of them is the one you'll gravitate towards the most to do Syn dihydroxylation. So a hydroxyl, again, is just making an alcohol. So a hydroxyl is an alcohol. So if you have 2 of them, you end up with a diol, which we sometimes call a glycol. You guys know ethylene glycol, right? If you watch the forensic files, you know what ethylene glycol is. There's always somebody poisoning a loved one or whatever with ethylene glycol because it tastes sweet, right? It has a good taste, but it's a poison. Anyhow, don't worry, they add a bittering agent to it now. Anyhow, so if you take ethylene and you do a dihydroxylation, you end up adding a hydroxyl to both vinylic carbons. Now, the anti-dihydroxylation is a 2-step process. Step 1, you treat it with this. What's that? This is called a peroxy acid, or peroxyacetic acid. And there's 2 examples of peroxy acids that we look at. So this is a peroxy acid. And in the next step, you just treat it with a dilute aqueous acid. But you form this interesting intermediate, which is called an epoxide. Okay, an epoxide. If you're the kind of person that has to Google everything, you might see this called an oxirane sometimes. But anyhow, you form this three-membered ring with an oxygen in it, this epoxide, which is pretty strained, and then you pop that open with acid, and you end up making a transdiol, right? You end up with the transdiol on account of anti-addition, right? The two hydroxyls are added to opposite faces of the molecule. And if you're wondering, you know, the nucleophile must attack from the bottom face in this case, right? Because the epoxide is pointing up, you would be 100% correct in that assumption. So let's take a look here. This mechanism here, I've never asked students about it, never have. Asked my students to draw the mechanism of the conversion of the alkene to the epoxide. However, it's one of the coolest mechanisms you see. It's a completely concerted mechanism, and it's 4 arrows all at the same time. You end up producing an epoxide and a carboxylic acid as a byproduct. So once you've got the epoxide, then you can treat it with acid. So if you're wondering, you know, what's this R group? What are the types of peroxy acids that we can use? There are 2 types that will show up in this class. I think that most of the time, David Klein will just write RCO3H like this, right? You just take a carboxylic acid and you stick an extra oxygen in there. I think that most of the time he writes this, or he writes MCPBA, okay? MCPBA. And I'll be honest with you, most of the time I'll write MCPBA, which stands for metachloroperoxybenzoic acid. It is probably the most commonly used reagent for forming epoxides in anti-dihydroxylation reactions like these, because it's a solid at room temperature, so it's easy to weigh out on a balance. And chemists love things that you can weigh out on a balance. Well, you guys know what acetic acid is, right? Acetic acid is the major acid found in vinegar. So this is acetic acid. Okay, well, if you stick an extra oxygen in there, you get peroxyacetic acid. Okay, so peroxy acid. Now you know a new functional group today, the peroxy acid. All right, so after you've formed the epoxide, which is a 3-membered ring, it's going to be pointing either up or down. Here's the mechanism for the formation of the diol from the epoxide. Step 1, you do a proton transfer. So you protonate this oxygen from the epoxide to make an oxonium, which is super hungry for electrons. Now, think about it. The oxygen has a positive charge, and it's more electronegative than a carbon. So it's going to want these electrons really bad, which is going to create a delta plus here and a delta plus here, right? Those 2 carbons are going to be really hungry for electrons. So you have a powerful electrophile. So water can come in as a nucleophile, produce this oxonium, which gets deprotonated by water. And there you go. There's your transdiol from the anti-addition. Okay, there we go. All right. This, in fact, it shouldn't say form the anti-diol. It should say form the transdiol, because trans assumes that it's locked, whereas anti necessarily doesn't assume that it's locked. Anyhow, so that's that reaction, okay? Again, all you have to do, let me give you an example. Let's say you take, so here's my summary, okay? Students love a summary, I think. You take cyclohexene, in the first step, you treat it with a peroxy acid. Second step, you treat it with dilute acid. You end up with a transdiol. So you would end up with this compound. Sorry, I'm drawing a little fast here. So you'd end up with this compound plus its enantiomer. That's the summary of everything that we just learned in that section. Now we got 5 minutes left. I want to cover Syndihydroxylation, which is just the addition of both hydroxyls on the same face of the molecule. The reason I can cover this kind of quicker is because we don't cover any of the mechanism. It is covered in the book. I have some curved arrows here. Yes, I do, which help you to understand why it occurs in a Syn fashion. However, I will not ask you this mechanism directly. Now, if you're wondering, are you going to summarize which mechanisms we need to know and which ones we don't? I'll tell you what, next class, I'll go over exactly which mechanisms you need to know. Okay, I'll put it on the list of the figure with all the reactions on it. So Syndihydroxylation, it just adds both hydroxyls on the same face of the molecule. There are a bunch of ways to do this. you can use this compound, which is OSO4. This is called osmium tetroxide. Okay, osmium tetroxide. And the reason why I showed this mechanism, since it's concerted, you can see why both of the hydroxyls end up on the same face of the molecule. You end up with this thing called an osmate ester. Then you get two options. You can either treat it with sodium sulfite and water, or you can treat it with sodium bisulfite and water, and you end up with the diol. You end up with a cis diol, right? Both hydroxyls are on the same face of the molecule. The problem with this reaction, and there's a big problem with it, is that this reaction, if you use sodium sulfite or whatever, it requires a stoichiometric amount of osmium tetroxide, and osmium tetroxide is very toxic. Okay, I've used it once in my life, maybe twice, and it is super toxic. It's expensive, but I'd be more scared of the fact that it's really toxic. And I'm not afraid of a lot of things in the lab. I'm afraid of chlorine gas, but anyhow, it's pretty dangerous. In fact, I worked with a scientist who refused to work with it. She simply said, "I'm not touching it. You don't ask me to do any reactions with osmium. I'm not doing them." So, is there an option? The answer is yes. In fact, the only time I've ever used osmium in my life, I always used NMO in conjunction with the osmium tetroxide. And if you're wondering, what's NMO, Mr. Dion? What's conjunction? What do you mean? Okay. Well, instead of using a stoichiometric, meaning like a 1-to-1 molar ratio of the osmium, which you would have to do if you did this kind of reaction, right, where you use in the second step, you would use sodium sulfite, or sodium bisulfite. To avoid that, you can use just like a catalytic amount of osmium tetroxide. That means just a little tiny amount, and you need something that's called a co-oxidant. So NMO stands for N-morpholine, N-methylmorpholine N-oxide. So this is called an N-oxide. That's a new functional group for you. I'll write the name out in the next lecture, N-methylmorpholine N-oxide. But that works to basically recycle the osmium tetroxide over and over and over. There's also this one here, which is tert-butyl hydroperoxide. I've never used that in my life, but apparently that's a good way to do it as well. So again, the benefit to these two are that they use a catalytic amount of osmium tetroxide because it's so dangerous. So basically, you end up with 4 ways to do this reaction. You can either do it the 2 ways that are shown here. You can use the first one, which was first step is OSO4. Second step is sodium sulfite in water, or you can use first step is osmium tetroxide. Second step is sodium bisulfite in water. And there's even another way to do it. So there's one more way to do it, and that is mentioned down here at the bottom. And it says here that potassium permanganate and cold sodium hydroxide will do the same thing. So to use that, you just use KMnO4 and sodium hydroxide, and you keep the whole thing cold, okay, at low temperature. The problem with this, right, and you can see that there's all kinds of problems with every reaction in organic chemistry, is that potassium permanganate is such a strong oxidizer that it just oxidizes everything. So if you're like, okay, well, why do I care? All it means is that if you have something else in the molecule that's sensitive to oxidation, it's going to oxidize it. Then you end up in trouble, okay? Can you use it on paper in this class? Hell yeah, go for it. All right. I probably